So let's jump into cylindrical coordinates. There's nothing challenging about the equations of motion, so let's do those first. And then we'll talk about how we can relate different coordinate systems. Because you guys, I've been telling you since the beginning of the quarter, you'll have problems with all three coordinate systems on them. That's where we are in the class, is we're going to have some problems where we have to use all three and relate them. And I'll tell you in a minute why we have to use them. But that's what we're going to go through and talk about. But first, let's do the easy part. The easy part is we're starting with the exact same equation. Sum of the forces is equal to mass times acceleration. The only difference is we're going to break up both of our forces and our acceleration in terms of the coordinates of cylindrical coordinates, which would mean sum of the forces in the r times ur plus sum of the forces in the theta times u theta plus sum of the forces in the z times uz equals mass times the acceleration in the r times ur plus mass times acceleration in the theta times u theta plus mass times acceleration in the z times uz. Okay, that gives us three equations of equilibrium, just like the other coordinate systems. Sum of the forces in the r is equal to mass times acceleration in the r. Sum of the forces in the theta is equal to mass times acceleration in theta. And sum of the forces in the z equals mass times acceleration in the z. Can anybody tell me what AR is? Do you guys remember? Second derivative of r with respect to time minus r d theta dt squared. That's my AR. My A theta is r second derivative of theta with respect to time plus 2 dr dt d theta dt. And then our AZ is just the second derivative of z with respect to time. Okay, so we see this as another tool. This might not be our hammer. Maybe this one's our drill. We get to take this one out when we see a problem that can easily be set up in polar coordinates. But sometimes you're going to need more than one coordinate system. For example, maybe you have something undergoing cylindrical motion. What does that mean? Well, it means that there's a radius, there's a theta, and there's a z. If you have a radius, theta, and z, something's undergoing cylindrical motion, you might be like, I'm just going to use cylindrical coordinates. But what if that thing weighs something? You need to bring in the weight. And generally the weight is going to be pushing straight down, which is typically an I and J, IJK. So we need a way to relate these and say, how can we find angles between the different coordinate systems? So to do that, we can set up a coordinate system as you see here. If you have a path, do you see the blue line? Blue line is the path. I'm going to put a particle right here, and it's going to move from there to here. This is going to move. I really should have made this bigger. There we go. Okay, so the particle is going to start at the red dot, and a second later, or a certain amount of time later, it's at the green dot. And we have a ds. ds is the arc length. How far did this thing actually travel? And we have a d theta, which is the change in theta for the rotation of r. We're going to use our arc length equation just like we have so many other times. And we're going to name a new angle. We're going to use psi as the psi is always going to be from the positive ur, which goes this way. Right? The ur is just an extension of r. You should always be able to find that. It's going to go between that and tangent, ut. It always goes between positive ur and positive ut. Now we're going to say, well, how can we find that? And how we find that is we say, well, I can make a triangle right here. See that little triangle? I'm going to blow that up. I've got a triangle where one side is dr. This side over, so that would be r d theta. And now we have to figure out how psi fits into this equation. So how does psi fit into this equation? Well, we have psi is right here. That one is psi. And if this is in the ur direction, that means it's parallel to my dr, right? So would you agree that, what is that, alternate interior angles? This one is also psi? So, how do I relate those three? How about tangent? Tangent of psi is going to be equal to r d theta over dr, which is equal to r over dr d theta. I just divided the theta on the bottom. Why? Because I can find both of these. I can find r and I can find dr d theta. Dr d theta is just the derivative of r with respect to theta. So if I can find r and I can find dr d theta, I can find psi. Why do I need psi? Because I need to be able to relate cylindrical coordinates to the path. I need to be able to relate cylindrical to normal tangential.